Good morning and welcome back. So, we've thus far, in the context of defiance, we've talked about the symporter as a really cool example of how to exploit this biological battery. In other words, I showed you that a concentration gradient can be set up, for example, by consuming some sugar. We have a concentration gradient, and what we did in that example was we showed very clearly, and in my opinion quite simply, how the presence of this gradient can be used to fuel parasitic reactions, which in this case was, or that case was, the pushing of sugar molecules up their gradient. And we saw that it didn't lead to any paradoxes. The sugar gets across the membrane, it's converted into ATPs, many of them, tens of them, 40 or something. And that energy, a few of those ATPs, if you like, can be used to pump the hydrogen ions back up their gradient to leave the battery poised to serve yet again as a universal sort of plug that you can plug into to drive other reactions, such as the ATP synthesis reaction shown here. So now what we're going to do is I want to talk about the ATP battery. And this vignette is going to be very brief, probably 5 minutes or so. And then what we'll do is we'll talk about a concrete case study, one of many reactions that depend upon ATP being held in a non-equilibrium state. But what I want to say here is I just want to give an introduction to the notion of the ATP as a biological battery. So it all comes down to one thing, really. And that is that the ATP, the ADP, and the inorganic phosphate are not at equilibrium. What do I mean by that? What I mean by that is that if there was a very nice statement, and I can't remember where it was. I think maybe it's in the book called Bioenergetics 3 by Nichols, and maybe it's Ferguson. But here's this. I'm going to paraphrase their statement. You could have an ocean filled with ATP, ADP, and inorganic phosphate. And I'm thinking of a particular view. There's a park right near the Cliff House on Ocean Beach in San Francisco. There's a park that kind of looks out over to your right is the Golden Gate, and when you're looking out, you're looking sort of due west. To your south is Ocean Beach, and then Pacifica and other places. It's a very out. You see, if you on a clear day, you see the Farallon Islands, and it's a very good place to see the vast expanse of the Pacific Ocean. I'm especially moved by it because my dad used to sail out of the Golden Gate on a 600-foot cargo ship as a navigator and go across the whole huge Pacific Ocean. And Nichols and Ferguson make the point that if you could have an ocean filled with ATP, ADP, and inorganic phosphate, and if they were at their equilibrium concentrations, they would be worth nothing in terms of fueling reactions. Literally nothing. You would not be able to do any work. And the thing that I think is important to say here is that, over the 19th century, we learned a lot about ways to extract work. So, Carnot had this idea of the Carnot cycle. He didn't call it that, but it has to do with the work you can extract when you have two reservoirs at different temperatures. And that's very important for our purposes. On the other hand, there are many examples where work is done isothermally. In other words, the temperature, there's not two reservoirs at different temperatures. There's basically one temperature for the whole system plus reservoir, and yet work can still be done, but because there's a different thing that's held out of equilibrium, and in that case the thing held out of equilibrium is concentrations. We've really already finished that by considering the case of the membrane potential, but in the context of ATP, ADP, and inorganic phosphate, the point is to have an excess of ATP relative to its equilibrium value, and the point of that is that the system always wants to, if you'll let me anthropomorphize, it wants to go downhill, converting some of that ATP into ADP and inorganic phosphate. It turns out that reaction is very slow, and it is catalyzed by the presence of a variety of different biological objects, usually proteins, that can take the ATP and speed up. What is the catalyst? A catalyst, if you like, is a bystander that makes a reaction go faster. So we'll speed up the reaction of ATP going down its gradient, if you'll let me call it that. And conceptually, really, this is the same idea as the transmembrane potential. It's not a different thing. So that's the introduction that I wanted to give. I just wanted to really make sure it's clear that this is not a mystery. It's not a magical wand. You have ATP hydrolysis. There's an actual simple Gibbsian interpretation, which is ultimately related to all of our familiarity with the idea that we can store energy and use it later to do work. I can hold up my iPhone, which I'm holding right here, and if I drop it, I could actually do work by compressing a spring. And if I had a switch, I could store that work by, once the spring was compressed, I could hold it in its position. I can, as shown here, store energy in the form of a transmembrane ion potential. And now I'm saying we could store energy in the form of a mismatch between ATP, ADP, and inorganic phosphate, where that ratio is constrained to take its out of equilibrium value. And just like with the previous example, we're going to constantly be pumping this thing to keep the ATP, ADP ratio fixed in its out of equilibrium value, such that, like the plug in the wall, we can plug into it universally with a whole series of parasitic reactions. In the same way that in this room, I have all these parasitic reactions. I have a heater, I have the charger, I have the lamp, I have all these things going on right now. They're all parasitic on Southern California Edison. So that's our introduction. What we'll do next is we'll think about examples, one example in particular, of an enzyme that gets phosphorylated. And we'll just try to understand the energetics of that situation.